Hello everyone, this is Dr. Hopkins with our next video, and we're going to continue our discussion of titration curves. But this time, we're not going to just have strong acid, strong base, we're going to add a weak acid. But the same would apply for a weak base. So if you titrate what we start out with, because we're in the low pH range, a weak acid, and we add milliliters of sodium hydroxide, or strong base, we get a titration curve that looks something like this, where we have pH versus milliliters of our titrant added. Now the difference is in a weak acid or a case with a weak base, you start with that weak acid, and as you add base, you generate some of the conjugate base of that weak acid, so we're effectively generating a buffer. And so there's a range, in this case, between about 3.5 to 5.5, where we're in what we call a buffer region, okay, where we're actually generating a buffer where we have both the weak acid and conjugate base. We have the same kind of somewhat rapid rise in pH as we approach the equivalence point. It's not quite as steep. Usually it's not quite as large in weak acid cases. But once again, the middle of that particular rise, the middle of that inflection, is the equivalence point, and the pH at the equivalence point, and the equivalence point in terms of milliliters added. And then once you go beyond that, we're in that excess strong base, so it's just similar to what we had for the strong acid, strong base titration curves. Okay, so what we're going to do is, once again, with the caveat that in lab this is much easier, we're going to go ahead and calculate the pH at a couple different points along a titration curve for a weak acid, strong base. In this case, our weak acid is going to be acetic acid, something that's very familiar in these lectures. And then we'll do at 0 milliliters of sodium hydroxide, 10, 25, and 30. So here we have set up the first problem, where we have our 25 milliliters of 0.1 molar, had to add that in, of acetic acid. We know the Ka, if I can get that right, is 1.8 times 10 to the minus 5 for that, so it's a weak acid. So basically we're doing this before we start. So we have a weak acid in water. This is a simple Ka problem. We've done many of these throughout the semester. So you would start with 0.100. Water, we don't care. So here we're doing our ice table. If we do this, 0, 0, plus x, so those are our x's, that's minus x, this is 0.1 minus x, and then our Ka is 1.8 times 10 to the minus 5 equals x squared over 0.1. I'm going to go ahead and drop this and assume that x is small in this case, and so my pH would just be the negative log of my x that I solved for, which in this case, without writing out all of the math, is 2.37. So before we start titrating, we would have a pH of 2.37. So here we have part B set up, where we've started with our 25 milliliters. We're 10 milliliters into our titration. So we've added 10 milliliters of 0.1 molar strong base. We're adding base, we have acid, that's going to be a reaction. We're going to have to do stoichiometry, so we have to calculate the number of moles, and here I've already calculated 2.5 times 10 to the minus 3 moles of our acid, 1.0 times 10 to the minus 3 moles of our base. So let's plug them in here and do kind of a figure out, based on that, the limiting reactant, which we already know. And that's going to be 0. We don't care about this. This is going to be minus 1.0 times 10 to the minus 3. So we're left with 1.5 times 10 to the minus 3 moles. Minus 1.0 times 10 to the minus 3. We have no strong base left, which is important. And we need to go ahead and calculate this, because this is the conjugate base of a weak acid. So it's going to factor in, and actually this should look somewhat familiar back when we were making buffers, where we started with the weak acid and we added a strong base in order to generate a buffer. So this, we can use the Henderson-Hasselbalch equation. I'm going to go ahead and write it out. pH equals pKa of the log of our base, our conjugate base, concentration over our weak acid. Okay, so notice we have these in moles. These are in concentration, but the volume is the same. So I can put those, so that ratio of concentrations is going to be the same if we use moles or if we use molarity. So I'm going to go ahead and just use molarity because I would divide both of them by, 35 or 0.035 liters. So anyway, let's do our pH. So the pKa, so 1.8 times 10 to the minus 5, take the negative log of that, and it was 4.74 plus the log, and then this would be 1.0 times 10 to the minus 3 divided by 1.5 times 10 to the minus 3. And if we do the math on that, we end up with a pH of 4.56. So after adding 10 milliliters of our strong base, we have a pH of 4.56. Here we have set up part C, which is the point where we add 25 milliliters of our strong base, which I've not written it out, but that's actually the equivalence point. So we have 25 milliliters of acid, 25 milliliters of base, and they're both the same concentration, so we have same number of moles, which I've plugged in for each one of these in our reaction. So we'll react away all of our acid, and we will react away all of our base, similar to like we did in the strong acid, strong base, except at this point we are left with 2.5 times 10 to the minus 3 moles of acetate. Now, and we have water, by the way, so we've generated water, but the strongest base or acid left is this. So we need to figure out, we need to figure out our concentration of this, which is 2.5 times 10 to the minus 3, divided by, 50 milliliters, which is 0.050 molar. So we have 0.05 molar acetate at this point. Now, how do we figure out the pH? Well, we have C2H3O2 minus. We also have water. That's in equilibrium. And we're going to generate OH minus and acetic acid. These are both aqueous, sorry. And then we would start with, now here we have a KB problem. And so we just generate an ice table, right? So this is 0.05, let's get that correctly. 0.050, 0 and 0, minus x, plus x, and then x, and then 0.050 minus x. So we just need to know KB, which is going to be KW divided by KA, which is KW is 1 times 10 to the minus 14. And so if we do that math, it's 5.6 times 10 to the minus 10. Okay, and then our two products, we have x squared, and this is 0.050. Once again, I'm going to assume that x is small because it's going to be small based on the k is very, very small as well. And so our x is going to be our OH minus concentration, which is x is equal to 1.7 times 10 to the minus 5, And that's our concentration. And so our pH is just 14 minus the negative log of 1.7 times 10 to the minus 5, which is equal to 9.23. So we have a pH of 9.23 at the equivalence point because we're left with a conjugate base. So here we have part D, where we're in the excess base range of the titration curve, and we've added 30 milliliters, so I've calculated the moles of OH minus, and I've done the reaction. Same reactions happened every time. And now at this point, our limiting reactant is going to be our moles of acetic acid, so that's going to disappear. We will also make 2.5 times 10 to the minus 3 moles of acetate, and we will get rid of 2.5 times 10 to the minus 3 moles of OH minus. But at this point, we are left with OH minus and acetate. And the stronger base is what's going to dictate our pH, because we have a weak base, or a conjugate base of a weak acid, and we have a strong base. So the stronger base is OH minus, and it's been circled. So we have 5 times 10 to the minus 4 moles, which we need to convert to concentration, times 10 to the minus 4 moles. And we have, 55 milliliters. That would give us our concentration, which is the same as what we did when we did the strong acid, strong base. And so our pH at this point is 11.96. Okay, so once we plug that in, it says 14 plus the log of our OH minus concentration from here gives us a pH of 11.96. So we've once again reached the point where we have excess strong base, and then that would be we have a really high pH. And finally, you can see I've kind of put all of our pHs. So we have our 4 pHs for our concentrations, or our milliliters added, excuse me. So we start at 2.37. That would be at the beginning of the titration if we were writing the curve. And then 10 milliliters is clearly in the buffer region, so it would be somewhere in here. But it's a pH of 4.56. We get to the equivalence point, and that's 25, right? So this is 25 there, and that's 9.23. So it's a little basic because we're left with the conjugate base of a weak acid, and then the excess base. So excess OH minus. So we'll do a titration curve like this with many more of these points. And now we'll wrap up with what we've learned from this. So once again, we've done titration curves. If you have a titration curve that has a weak acid, we did not show over a weak base, but they both would have a buffer region because you would generate the combination of a acid and conjugate base. We can determine the equivalence point of an acid-base titration, even in this case, and each point is just simply the same kind of calculation that we knew how to do before. So until next time.